So start. Maybe in the meantime, people will join. Uh, so welcome to live session 3. And today what we will do is we will go through different welding processes like gas tungsten arc welding, gas metal arc welding, different modes of metal transfers. Am I audible, right? Am I audible?
Yes, sir.
Okay. So we will go through different welding processes like gas tungsten arc welding, gas metal arc welding, different modes of metal transfers. We will again go through we will again go through constant current power source, constant voltage power source. So feature generally used in gas tungsten arc welding. And then briefly we will cover up this laser welding, submerged arc welding, electroslag welding, whatever has been covered in our earlier lecture videos, right? Okay. So initially to start with, I want to start with some concepts on residual stress and distortion, because these two parts are integral aspects in welding, right? So we will first try to explain in terms of what happens in residual stress or what is residual stress or distortion in terms of uh, process mechanism or how does it develop, why does it develop, right? That will help us to understand which processes will end up with reduced residual stress or reduced distortion or large distortion, these kind of concepts, right? So initially we will start with, let me take this one, residual stress, right? So why does it develop residual stress? This is simply an effect of heating and cooling in welding, right? So this is result of some kind of restraint to thermal expansion and contraction by the metals to be welded, right? So there will be expansion because of thermal expansion coefficient property of the material. There will be expansion during heating as well. There will be contraction, right, during cooling. So let us consider rectangular bar. So let me consider a rectangular bar, something like this, and this is my welding region. Let's say this is my welding region. Okay. So let us consider that this rectangular bar is uniformly heated and cooled. Right. So whenever it will be heated, the material will get expanded, right? And it will become larger in length, width, and thickness. As simple as that. And upon cooling, what will happen? The material will get contracted, right? And each of those dimension will return to its original value. Now, if you insert the bar between some rigid restraints, so if we insert some kind of rigid restraints, let's say, so that lengthwise expansion cannot take place and we are repeating the thermal cycle. So we will insert those rigid restraints in such a way that lengthwise expansion will not take place. Lengthwise. So we are restricting the length by restraining the length and we are heating the material, right? So upon heating, all of the expansion is restricted to the width and thickness, but the contraction upon cooling will start occur uniform. No, so that will happen. Now, in this figure, in this figure, so here we are welding two plates, right? We are welding two plates over here. As the weld is produced, so you are having liquid region whenever you are doing melting. So that liquid region conforms to the shape of the mold, and the adjacent material becomes hot and it will try to expand. So that was my heat affected zone, right? Heat affected zone will try to expand, right? And the molten pool that can absorb expansion of the plate, which is perpendicular to the weld line, right? And that weld tends to be restrained by the nearby plate material, whatever is there, this nearby material, that expansion will be restrained by that nearby plate material, right? Which will remain cooler and stronger. So this resistance is often sufficient to induce deformation of the thermally expanded heat affected zone, right? So how does it look like in terms of residual stress? So over here, it will have, it will try to expand, right? Sorry, it will try to expand. So it will feel tensile residual stress, and the adjacent region, they will restrict that tension, and over there I will feel compressive residual stress. Agree? Now, if we try to understand in terms of graph or profile of the residual stress, it will look something like this. So let me take this page. So over here, this is my plate to be joined. Over here, I was having tensile residual stress. Over here, I was having compressive. So my profile will look something like this. Correct? So this is my, these two are compressive residual stress. Let's say A and B are compressive residual stress. And at C, it will be tensile one. Correct?
Yes, sir.
Now, what is the effect of thermal stress? So, because of those thermal stresses, distortion will happen. So, let's say you are doing some V group butt weld. So, this is my V group butt weld. If there is some kind of residual stress because of heating and cooling cycle, it will take some shape like this. There will be some kind of linear distortion, or it can be angular distortion also. So, this is theta. So, there will be angular distortion also. If this is a fillet welding, let's say this is a fillet welding. So, this was my initial structure. This is a fillet weld. and my final structure will look something like this because of those residual stresses, right? And how these things can be minimized. So how you can minimize the distortion of your welding joint. So the basic principle is you have to somehow reduce your total heat input to the weld, right? So either you can do some pulse heating or you can do some. So I'm coming into that aspects. Uh, so the basic fundamental procedure is to you have to somehow minimize the total heat input, but at the same time you have to go to your melting point so that the melting takes place and welding is happening properly, right? Now, apart from that, apart from that, you can do some process called cleaning, right? So this is a procedure. Uh, so reduction of distortion due to residual stresses, right? So how we can do that? I was saying that we can reduce the total heat input. This is one aspect. Another aspect can be peening. So peening means what should I say? Uh, this is a procedure to balance the resulting thermal stress by using some hammering hammering procedure. So we will hammer the weld metal such that there will be some compressive residual stress will be generated, which can reduce the crack formation and those aspects, right? So as the weld bit surface is hammered with the pinning tool or the material, the metal will get flattened and it will try to spread up, right? So by that procedure, you can reduce your tensile residual stress or crack formation if anything is happening in your welding. Another aspect can be another aspect can be depositing some weld metal in some specific pattern. So if you are doing joining, so you can deposit your weld metal in some specific pattern so that this tensile and compressive residual stress will balance each other, right? So depositing, right? So people also do something called stress relief heat treatment. So, so yeah, so you can do some stress relief heat treatment prior to some kind of machining operation if you want to do some machining over a welded material because of residual stress. There can be failure of the weld metal before the machining. So some kind of stress relief heat treatment, some kind of pinning operation need to be done uh, to remove those residual stresses and then do the post operations. Right? So this was something on brief introduction to residual stress and distortion. And then we will move to this gas tungsten arc welding part. So what is that process? What is the basic mechanism of that process? Those things, right? Now in gas tungsten arc welding, let me rub this off. If you have any question, you can ask.
No, sir.
So we'll talk about gas tungsten arc welding, which is a process, as you know, that melts and joins metal by heating them with an arc established between a non-consumable tungsten electrode, right? So this is the catch, non-consumable tungsten electrode. So we'll be using non-consumable tungsten electrode and the metal workpiece, right? My net got disconnected. Am I audible?
Yes, sir.
Yeah, thank you. So we'll be using a non-consumable tungsten electrode. Let me draw some picture. So I'll be having some electrode like this. There will be this shielding gas nozzle, something like this. I'll be producing arc, and then um, there will be this metal droplets. I can use some feeler rods also, and this is my shielding gas. Right? So over here, the torch holding the tungsten electrode is connected to a shielding gas cylinder, right? As well as one terminal of the power source. Now, the tungsten electrode over here is usually in contact with some water-cooled copper tube. Yeah. So the tungsten, some reason my Wi-Fi is. For some time, I'm just connecting it. Yeah. Is it better now? Am I audible? Hello?
Yes, sir. Ari, sir. Provide.
Okay, thank you. So what I was talking about, uh, yeah, the tungsten electrode is usually in contact with some water-cooled copper tube, and which is connected to a welding cable from the terminal. So, so basically, it looks something like this. Let me draw. I will have a shielding gas cylinder. So let's say this is my shielding gas cylinder. It can have some flow meter to measure how much is the pressure of the gas. Let's say this is flow meter, and this is my torch. So this is my welding torch. This can be a feeder rod. This is my workpiece. This is connected to one end. My torch is connected to the other end. So this is my cable 1. This is my cable 2. Right? This is how it will look like. Now over here, uh, this allows both the welding current from the power source to enter the electrode and the electrode to be cooled to prevent work overheating, as it is connected to those copper cable or copper contact tube, as I was saying. Now over here, the workpiece is connected to the other terminal of the power source, right? Through a different cable. Now the shielding gas through the torch body, and the shielding gas, it goes through the torch body. So this one, the shielding gas goes through the torch body, and it is directed by a nozzle toward the weld pool. It is directed by a nozzle towards the weld pool to protect it from the air, right? So protection from the air is much better than what happened in gas tungsten arc welding or than in shielded metal arc welding, because over here an inert gas such as uh, this had been discussed in our earlier class also.
Helium, neon,
Right. So
argon.
we'll be use some inert gas such as argon or helium that is usually used as shielding gas over here, right? And that is directly we are providing directly towards the weld pool. So for this reason, gas tungsten arc welding is also called tungsten inert gas welding, right? Now there are different polarities come into picture to do this operation. What are those polarities?
Reverse polarity and straight.
Reverse polarity and straight polarity. So let me
Sir,
write down this.
sir, which material used for filler metal rod?
You can use similar metal or dissimilar metal based on your application.
Okay, sir.
So in terms of polarity, we will be using direct current electrode positive and direct current electrode negative. Right? Now in direct current electrode negative, this is also called straight polarity. Right? And this is the most common polarity in gas tungsten arc welding. So as the name suggests, over here the electrode is connected to the negative terminal of the power supply. So if this is my electrode, if this is my workpiece, this will be connected to negative terminal, this will be connected to positive terminal, right? Now here electrons are emitted from the tungsten electrode. Because this is connected to the negative terminal, there will be tendency of electrons to be emitted from the tungsten electrode. So I will be having electrons emitting from the tungsten electrode, and that will be accelerated while traveling through the arc. So I have talked about well enough in terms of arc initiation, what happened in thermoionic emission. These things have been already discussed, right? So whenever these electrons are accelerating through this arc, there will be significant amount of energy. What that calls, what that energy is called, that is called work function or thermoionic work function, right? That is required for an electron to be emitted from the electrode. Now, when the electron enters the workpiece, an amount of energy equivalent to that work function is released, right? This is why in gas tungsten arc welding with DC electrode negative, more power is located at the work end of the arc and less at the electrode end. So whenever or whatever will be connected to the positive end or anode side, two-thirds of the heat will be generated at the positive side, two-thirds of heat will be generated at anode side, and the rest, which is one-third, will be generated at the cathode side. Right? So this is on direct current electrode negative. Now what happens with direct current electrode positive? This is also called reverse polarity. Let me take this. This is also called reverse polarity. Over here, the electron is connected to the positive terminal of the power source, right? So here heating effect of the electrons is now at the tungsten electrode rather than at the workpiece, because your electrode is connected to the positive terminal and workpiece is connected to my negative terminal. So heating will be more at the tungsten electrode side, right? So what will happen as a result? So consequently, a shallow weld bead will be produced. So reverse polarity will give me a, because heating is not much at the workpiece side. So the weld bead what it will produce is shallow in nature, right? Furthermore, as I was saying, a water cooled electrode must be used in order to prevent the electrode tip from melting. So water cooled electrode must be used. Right? Now, what electrodes we can use? So, in general, with tungsten electrode, we mix up cerium or thorium, right, to have better electron emissivity or better current carrying capacity or uh, resistance to contamination than pure tungsten electrodes. So, as a result, if you are mixing these materials with pure tungsten, uh, the starting of the arc will be much easier. The arc will be more stable, right?
Yes, sir.
Okay. Now, can you name different variants of gas tungsten arc welding? So, whatever we were talking about as of now is conventional gas tungsten arc welding. Let me take my check. So, can you name different variants of gas tungsten arc welding? So, we will be talking about different variants of gas tungsten arc welding. What are those? So, in terms of variants of gas tungsten arc welding, we can have a pulsed gas tungsten arc welding. We can have something called hot wire gas tungsten arc welding. We can have something called activated flux, GTW, right? So what is pulsed GTW? This is just a pulsed current which alternates between high and low current levels. So this pulsing creates a series of short and intense arcs followed by periods of lower energy. So it will have some kind of cycle like this. So if this is current and if this is time, you'll have some cycle like this. And coming into what are those things? So basically, you will have some improved control. This pulsing will allow for better control of heat input, right? And the well bit characteristics. So what is the benefit of providing this pulsed operation rather than uh, if you are doing some continuous current supply? So because you are controlling your current as a pulsed current, you are reducing your total heat input. So H net will get reduced in pulse GTW, right? It minimizes your thermal distortion. It will help in welding clean materials. Clean materials can be welded. And also, the technique will often leads to improved penetration and beat profile. So, in conventional GTAW, how will your bit look like is something like this. It will be much wider. So, the weld bit width will be, let's if this is D1, this is pulsed operation, this is D2. D1 will be much greater than D2 and H1 will be H2. So the penetration will be higher over here. You will have less spatter also. The controlled arc will reduce your spatter and improves your overall appearance of the weld. Yeah. So what do you have over here? As I was saying, you'll have a background current. So this we call it as, let me rub this up. You'll have a background current, you'll have a peak current. So background current will maintain the arc and it will help to control the heat input. minimizing overheating and distortion, those things. And peak current will provide the necessary heat to melt the filler metal and the base metal. So I will be having a background current, and then I will be having a peak current, something like this. So this is my T. Let's say this is TP, the time for which the current is maximum, and this is TB, time for which there will be this background current. So there will be some average current with which I will do my processing for welding, right? Any question?
No, sir.
Okay. So this is something on pulsed process, pulsed GTAW. We were also talking about what next? Hot wire GTAW. What is there in hot wire GTAW? So in hot wire GTAW, the main catch is you're using a feeler wire. Why you are using a feeler wire? To increase your deposition rate, right? So in hot wire GTAW, your feeler wire, whatever you are using, that is preheated. That is preheated to a temperature that is, of course, close to the melting point before it is introduced into the weld pool. How you can preheat the metal? How you can preheat the feeler wire? Um, so I will go to over here. So I was talking about this feeler wire. What we will do, we will do some electrical heating of the feeler wire. So there will be some external heating arrangement uh, where there will be this I square R heat, I square RT, Q equal to I square RT, that will be generated because of that electrical heating of that feeler wire, right? And that preheated feeler wire adds some extra heat that is directly to the weld pool, and it reduces the need for excessive heat from the welding arc alone, right? So what are the benefits over here? What are the benefits of hot wire gas tungsten arc welding? Can you name few? One I have already mentioned, deposition rate will be higher. By preheating the feeler wire, the welding process becomes more efficient, right? So extra heat that reduces the overall energy required from the arc to melt the feeler and base metals. So my efficiency will be much higher, and it is also useful for welding thicker materials. So also useful for welding thicker materials, thicker materials where additional heat is required to achieve proper fusion. And then what next? We have activated flux. So this is a spatial variation of GTW which enhance welding process through use of some kind of activated flux. Over here, a flux material is applied to the surface of the base metal before welding, right? So this flux can be in the form of paste, it can be in the form of powder, it can be in the form of coating. So during welding, that flux will react with your weld pool and the base metal. It will enhance your welding process, and basically the flux will help in terms of deoxidizing the metal. It will stabilize your arc, and so whatever is the benefits of this, the benefits of flux core arc welding. So whatever will be the benefits of flux, those functions will be done by these activated flux things, right? So that will benefit in terms of, let me write down over here, activated flux. So what we'll have some improved penetration. So the flux will help in increasing the penetration of the weld, right, by promoting a deeper fusion. So we know about Marangoni convection, right, which controls the weld pool flow because of some change in surface tension, right? So if this is your weld bed, where the temperature will be higher, the temperature will be
Center.
the temperature will be higher at the center. So
Center.
let's say this is a T center, this is a T periphery. So T center will be higher than T periphery, right? So over here my surface tension will be higher. Over here my surface tension will be lower, right? So in conventional arc welding or in conventional uh, gas tungsten arc welding, because of Marangoni convection, the fluid will flow like this. The weld metal will flow like this. However, because of using those activated flux, it will change my surface tension. So wherever there will be higher temperature, there will be higher surface tension, and wherever there will be lower temperature, there will be lower surface tension. So it will basically change your direction of the convection. This we will call reverse Marangoni.
Sir, is it also change direction of flow of molten metal या flare material from center to lower surface tension?
That's what I was talking. So this is called reverse Marangoni because it is changing the direction of the flow. So it will come from this to this, something like this. So from periphery to the center, and it will extend towards the thickness direction. So the depth will be higher over here, or the penetration will be higher over here because of the reverse Marangoni,
Okay, sir.
right? And also the flux can act as some thermal barrier, so which will allow some more controlled and localized heat input. So over here, I'll be having some localized heat input because you are having some flux covering that uh, covering that welding arc that will act as a thermal barrier. And You can also join both thin and thick needles. So this activated cluster welding. Okay. So let's let's go through some questions initially, and then again we will start discussion on some theories. Okay. Don't know why people are not joining. So whatever we have discussed till now, let us do some quick question and answer for this session. So what does gas tungsten arc welding generally use? Does it use straight polarity or reverse polarity or constant current power source? Anyhow, I have talked about constant current power source and constant voltage power source in my previous video. Do you have some idea on constant current and constant voltage power source?
I think constant voltage power source.
Why? We are saying that in gas tungsten arc welding, we are using a non-consumable tungsten electrode. So is there any need for constant voltage power source? So constant voltage power source is generally used when you want to use some self-regulating arc, or if you want to maintain your arc length. So let's say your electrode is consumable in nature. Say your electrode is consumable in nature. What will happen? So in semi-automatic arc welding process, the arc is maintained between some workpiece and your wire, which is driven forward at constant speed. So there will be some spool kind of thing to which you will continuously feed your electrode, and then you'll have some welding torch, something like this, and you'll melt it through arc, and then you'll have workpiece, right? So you want to maintain your arc length constant so that there will not be any kind of arc blow because of changing voltage suddenly, right? So if you are using some consumable, if you are using some consumable electrode, at that point of time you should use constant voltage power source. Constant voltage power source. What will happen? Because if there is an increase in your arc length, if there is an increase in your arc length, what will happen for voltage? It will increase the voltage, right? And as a result, the current will fall down. Now, the melting rate being dependent on the current, an increase in the arc length that will causes a decrease in melting rate. Got it? So, if the reduction, if the reduction in the current due to an increase in the arc length is significant, the melting rate decreases. right? So arc length will return to its original value. That's what we call as a self-regulating. So over here in gas tungsten arc welding, we generally use a non-consumable tungsten electrode, and we will prefer a constant current power source. For gas metal arc welding, yes, the constant voltage power source will be much more suitable. And what about this reverse polarity or straight polarity? What polarity will be used in gas tungsten arc welding? So because this is non-consumable electrode in gas tungsten arc welding, we don't want to consume the electrode. We don't want to heat produced at the electrode side. So the workpiece side should be the positive side. So the straight polarity is used in gas tungsten arc welding. Agreed?
Yes, sir.
So in gas tungsten arc welding, we will be using straight polarity and a constant current power source. Now, which of the following uses reverse Marangoni flow?
Activated flux GTAW.
Activated flux GTW. Correct. So A is the correct option. Let's do some numerical. Let's do some numerical. This is very simple. Uh, this will be a quick numerical. So here I have mentioned that in a gas tungsten arc welding process, my background current is 10 ampere. So let's say IB is 10 amp, IP is 400 amp, which is peak current, and then I'm talking about duty cycle. So duty cycle is basically is defined as it actually defined as T on by T on plus T off. But over here, it's not exactly off time. This is background time. So I'll be using it as T peak by T peak plus T background. This is given as 0.4, right? And then
Plus TB.
I'm saying that time for applying the peak current is 10 millisecond. Time for applying the peak current is 10 millisecond. What is the average current for the process? So average current will be what? It will be the energy for background plus energy for peak, that divided by total time, TP plus TB. Now if all the equations are known, can you keep calculate and give me the answer?
Sir, TB also unknown.
You have to find out TB from this.
Duty cycle.
Yes.
Okay, okay, sir. Sir, I will calculate after the class.
Okay, no problem. So, yeah, you got the concept, right?
Okay, okay.
So, if TP is 10 millisecond, TP plus TP is 0.4, 0.4 TP. It's something wrong. Sorry, I know the TP. So, 4 TP, 4 plus 0.4 TB is equal to 10. 0.4 TB is equal to 6. TB is how much? 15 millisecond. So if you know TB is equal to 15 millisecond, you can simply put down your value over here, right?
Yeah.
10 into
Okay.
15 plus 400 into 10, that divided by 25. So this will give me some value, 150 plus 4000, that divided by 25 amp. Okay. Okay. Now we will come to this gas metal arc welding.
Okay.
What is the difference between gas metal arc welding and gas tungsten arc welding? So over here you are establishing your arc between a continuously fed feeler wire electrode and the metals. For gas tungsten, it was a non-consumable electrode. Over
Yes,
here, this is a continuously fed feeler wire, right?
yes,
So
sir.
you will have some, again, you will have some shielding gas cylinder. So this is my cylinder, which will have some shielding gas. You will have some flow meter or regulator. Then I will have some welding torch, something like this. This is welding torch. This is workpiece. This is my, let's say, welding direction. I'm just making a schematic. This is workpiece. This is welding torch. And how we will feed the wire? We will have some wire reel or spool kind of thing. So that will rotate and it will continuously feed the feeder wire through that welding gun, right? And it will have some, of course, wire drive and control. So I will have some drive control mechanism for that wire. It could be some through rollers or something like that. And I'll have the power source, right? One will be
Yes,
connected to positive, one will be connected to negative. This will be rotating. It will continuously feed the feeder wire, right? Now, shielding of the arc and the molten weld pool that is obtained by using inert gases. So we also call it metal inert gas welding. Over here also you are using inert gas like argon or helium, right? Sometimes non-inert gases like CO2 also used, and most widely this is used for aluminum alloys. Okay, so gas metal arc welding is most widely used. You can mute yourself for aluminum alloys. Okay. Now, in terms of shielding gases, as I was saying, argon, helium, and their mixtures are often used for non-ferrous metals as well as for stainless or some kind of alloy steels. Right now, the arc energy is less uniformly dispersed in an argon arc than in a helium arc because of lower thermal conductivity of argon. So I will mention these things. So thermal conductivity of argon is less than helium. That's why the arc energy will be less uniformly dispersed in an argon arc than in a helium arc, right? And so basically, consequently, what will happen? The argon arc plasma has a very high energy core and uh, less thermal energy. This will help to produce some stable axial transfer of metal droplets through an argon arc plasma. So the arc stability will be higher for argon compared to helium. Now, with ferrous metals, if you are using ferrous metals, helium shielding may produce some kind of spatter, and argon shielding may produce some kind of undercutting. So this has been observed through lot of experiments. People have done lot of experiments by using different kinds of shielding gas for different kinds of material combination, and these have been figured out through lot of researches. Right. Now, in terms of modes of metal transfer, modes of metal transfer, what are different metal transfers you can think of or you have gone through? You have globular metal transfer, you have spray metal transfer. What else? Pradeep, can you please mute yourself? So these are my three kinds of metal transfer, right? We have already gone through these different modes of metal transfer. Now, now in globular transfer, so what will happen is there will be discrete metal drops close to or larger than the electrode diameter. So that's how we will characterize a globular transfer. It can be close to or larger than the electrode diameter that travels across the arc gap during this gas metal arc welding, right? So for globular metal drop dia is greater than equal to the electrode dia, right? So how will you characterize a globular transfer? This is often is not smooth and it produces scatter. So this is how you can characterize a globular transfer. This is not smooth and spatter formation will always be there with globular transfer, regardless the type of shielding gas what you are using, right? Now in spray transfer, in spray transfer, above a critical current level, so my current level will be much higher. Above a critical current level, the small discrete metal drops that will travel across the arc gap under some influence of electromagnetic force. So under some influence of electromagnetic force, it will discretize your metal drops. If it was globular or the shape was something like this, it will discretize the metal drops in small droplets, right? And the current will be much higher what we see for globular transfer. So over here, the current for spray transfer is much higher than the current for globular. And finally, there is this short circuit transfer. Over here, your uh, molten metal at the electrode field is transferred from the electrode to the weld pool when it touches the pool surface, right? Basically, the short circuiting is happening. So the short circuit transfer encompasses the lowest range of welding current and electrode diameter. So short circuit transfer is characterized by lowest range of current and electrode diameter, right? So basically, it will be producing small and very fast freezing weld pool that will be desirable for welding thin sections. So short circuiting transfer is desirable for thin material joint. Any questions? So what I have talked about in terms of metal transfer for short circuit transfer that is promoted by the lowest current as well as the voltage also. It can use CO2 shielding gas for your gas metal arc welding. Now the advancing electrode that will make direct contact with the weld pool and the short circuit will cause some rapid rise in current and uh, big molten globes from on the tip of the electrode and then it separates. So basically, it will look something like this. So let me draw this. So whenever it touches, because of surface tension, it will detach from the electrode, right? If the voltage and amperage, if you are increasing your voltage and amperage, the mode becomes one of globular transfer. So over here, the electron melts from the heat of the arc and metal drops with a diameter, as I was saying, equal to or greater than the diameter of the electrode square. Now, what are the forces which will govern for globular transfer? Mostly gravity and electromagnetic. So these are different forces, right? Which will be this, uh, which are the primary reason for separation of a droplet. So if we try to figure out in terms of um, free body diagram, free body diagram in terms of what are different forces which will be acting on a metal droplet. So if this is my electrode, if this is my electrode, and if this is my arc, so let me take some other color. If this is my arc, this is my arc, this is my workpiece. So one will be gravity force, one will be surface tension force. What else? You'll have Lorentz force because of electromagnetism. You can have some, we call it pinch force also, which will act vertical to that arc surface. So these are different kinds of force. Those are the major force that will take part in the separation of the arc, right? So the force of gravity may be a retaining or detaching force, right? Depending on whether the electrode is pointing upward or downward. But the surface tension always tends to retain the liquid drop at the tip of the electrode. So this force depends on the radius of the electrode, the capillary constant, density of the liquid metal. Those parameter will come into picture when you are talking about this surface tension force. You know, electromagnetic force known also as the Lorentz force, as I was saying, and this will be always set up due to the interaction of the electric current with its own magnetic field, as you know. And this force acts in the direction of the current, right? When the cross section of the conductor is increasing in the direction of the current, this will also act in the direction of the current, this electromagnetic force. So these are the force which will be resulting in detachment of that metal transfer and resulting in different modes of those metal transfer. Okay, so we were in question 3. Which of the following uses highest welding current? Which of the following uses highest welding current?
Spray metal transfer.
Spray metal transfer occurs with highest welding current, right? So I'm I'm just taking it over here, right? So C is correct option. Okay, there are few very fundamental numericals. We will do this 5 and 6 first. This will not take much time. So Let's do that. Over here, I'm saying a 90 long sheet is to be welded with MIG welding process. Uh, Heat input per unit length, how much? 10 joule per mm. You have some efficiencies, melting efficiency. These have been already discussed. What is melting efficiency? What is heat transfer efficiency? So fine. Eta heat transfer is 0.8. Eta melting is 0.6. What is the electrical energy consumption? The sheet length is L is 90 mm. So what is my total heat input? It's simply 10 into 90. This much of joule. So 900 joule is my total heat input. Now if you are having some efficiency, so there is some heat transfer efficiency, there is some melting efficiency. What will be the energy consumption then? So my heat input required per unit length is 10 joule per mm. So basically total energy consumption, if we multiply it with the efficiencies, I will get the actual heat input required for melting. Agreed or not? Yes or no?
Yes, sir.
If this is correct, so let's say my total energy consumption is X joule. So X into 0.8 into 0.6 will be equal to 900. So I'll get some value of X. I don't know how much. Can I calculate quickly? So 900 by 0.48. This. It's 1875 joule, right? If you have any question, please ask. We're moving fast now. Next, again, this is again a simple problem. So we say electrode diameter is used is 2 mm. So D electrode is 2 mm. Wear feed rate is 3 meter per minute. Now I say weld bit total area. Area is 31.4 mm square. So what is the welding speed used in the welding process? So you know the area of the weld bit. So if I know the area of the weld bead and the welding velocity, this will govern me to which quantity. Hmm? This is the volume, right? Volume per unit time. Basically, this is the filling rate of the weld bead. Is it not? And so if you have area, if you have velocity, you can find out the volume of the weld bead, and that will be equal to your, the electrode diameter, the wear feed rate. So that will be equal to the melting rate of the electrode. So it will be basically pi by 4 into t square into the feed rate. So this is 3000. This is in meter per minute. So I'm doing it in millimeter. So 31.4 mm square into velocity, that will be equal to pi by 4 into 2 square into 3000. This is in millimeter cube per minute. Understood?
Yes, sir.
Great. So I'm not doing the calculation as of now. I hope the concept is clear. Should I move on? Okay, I'm moving on then. Huh. Okay, so here I ask cold metal transfer in gas metal arc welding. I have not talked about cold metal transfer welding as of now. This is basically a variant of MIG welding, right? Metal inert gas welding. So it utilizes a unique control system. It utilizes a unique control system to improve your welding. Right? So basically you are controlling the transfer of your weld wear and the heat input to the workpiece. So that's what you are doing in cold metal transfer. Of course, this is not cold as the name suggests, but because of some inherent feature of cold metal transfer welding, you can provide some low heat input, low distortion, improve weld quality. So those aspects are there because you are providing low heat input. That's why it is named as cold metal transfer welding. No. Now in CMT welding, the welding wear is precisely controlled as it is fed into the weld pool, right? So basically over here, wear will be alternately pushed and retracted. So it will something like this. So gas metal arc welding is a type of short circuit metal transfer actually. Now in short circuit metal transfer, let's say this is my electrode. This is my electrode, okay? And this is producing some metal droplet and it is touching the workpiece. And whenever it touches the workpiece, the current will drop down. So this is while touching, and this is after touching. This is current, this is time. So this is how you will control your feed rate or the wear feed rate. in such a way that you can help in managing the heat input, which will be crucial for welding, uh, some metals. So basically, uh, the ultimate result is low heat input, minimized minimized heat distortion. So this is the machine should be some equipped with some good amount of advanced control system for wire feeding and heat management, right? That should be there, and also the advantage is this is stator free. So the spatter will be reduced for CMP welding. Okay, so this is a type of short circuit metal transfer, as I was saying. This is a similar type of numerical as we are doing. So over here, I say that I have my current as 200 amp, voltage as 25 volt, welding speed is known, wear die is known, wear feed rate is known, you know the thermal efficiency also. So I need to find out the area of the cross section. So in a similar way, as I was doing for the earlier numerical also, we will find out the volume of the weld. Now, so you can find out the volume of weld. So this is pi by 4 into d square into L. D is your wear diameter, L is your wear. L is wear feed rate. So I will end up with some pi by 4 into 1.2 square into 4,000. So my wear feed rate is 4 meter per minute. So this will be in some millimeter cube per minute. This is my volume. So how you can find out the cross-sectional area? Then area is volume by speed. Any confusion? So you'll find out the volume of the weld speed, volume of the weld metal as this as mm cube per minute, and you have your weld speed, which is 180 per minute. This is cube per minute. Can you find out the area then? Hmm? Is there any confusion? It is the same numerical what we are doing in this question, question 6. I don't think there should be any confusion as such. Any response? Guys, understood? If not understood, then we'll Okay. So finally we'll move to few questions. Which welding process requires bare metal electrodes and granular flux? As you know the answer, of course. So, what is the correct one? Submerged arc welding, right? So, this is a process that melts and joins metals by heating them with an arc, which will be established between a consumable wire electrode and the metals. And over here, your arc will be shielded by a molten slag, and there will be a granular flux, right? So this differs from the arc welding process discussed so far in that the arc is submerged and invisible over here, right? So the flux is supplied from a hooper which travels with a welding torch. So no shielding gas is needed because molten metal is separated from the air by your molten slag and granular flux. And most oftenly used is electrode positive, or if electrode is positive it is reverse polarity. Because you are using a consumable electrode, you are using reverse polarity, right? So what are the advantages and disadvantages? So protecting and refining action of the slag, that will help in producing some clean weld in submerged arc welding. Since the arc is submerged, there will be low spatter, heat losses will be low to the surrounding. So heat losses to the surrounding air will be basically eliminated even at high welding current, right? And both alloying elements and metal powders can be added to the granular flux to control your old metal composition. It can increase the deposition rate. So all those aspects are there for submerged arc welding. So the deposition rate will be higher. I'm not mentioning all those things. These are very well known and common aspects of, these are well known, right? Then you have uh, electro slag welding also. You have electro slag welding also. So in electro slag welding, this is a process that will melt and join metals by heating them with a pool of molten slag, right? That will be held between metal and some continuously feeded filler wire electrode. So I'll be using a molten slag in electro slag welding. That is the main aspect of a electro slag welding. So the weld pool will be covered with that molten slag, and it will be moving upward as the welding progresses, right? So there will be some pair of water-cooled copper shoes, one in front of workpiece, one can be behind, and that keeps your weld pool and molten slag from breaking out. So it is similar to submerged arc welding uh, in some kind. So over here, your molten slag will be protecting the weld metal from air, and it will refine it, right? Strictly speaking, it is not an arc welding process because arc exists only during the initiation period of the process. It is when the arc heats up and the flux and it melts it, right? And the arc is then extinguished. So initially the arc will be there. Initially arc gets generated and then extinguishes. So what happens next? Then the resistance setting will come into picture. So whenever the arc is getting extinguished, the resistance heating generated by the electric current that will be passing through the slag that keeps it molten. So, right? So in order to make your heating more uniform, electrode is often in some kind of oscillatory in nature. So electrode can be. Can you give some example through which where electroslab welding is often used, or what are some applications? Hmm? Electroslab welding is used if you are doing some welding of ship hulls or some storage tanks, big storage tanks, thick welding mainly. Okay, so this is also a simple question. Friction welding is used for joining of cylindrical dissimilar metals. Gas metal arc welding. AS is 3. Non-constant. AS is 1. Q is 3. R is 2. Right? These are all covered. Anybody have any question till now? Okay. So if there is no question, I was talking about pinch effect. Pinch effect is caused due to C, electromagnetic force. And then there was something on this laser welding. Anybody awake here? So laser beam welding is a process. Of course, you'll be using laser beam over here. Uh, this can be either solid state laser or it can be a gas laser. So in either case, the laser beam will be focused and directed by some optical means, right, to achieve some high power density. So in solid state laser, single crystal will be doped with some small concentration with some transition element. What is a solid state laser? I hope you have heard of Nd:YAG, right? So in a YAG laser, the crystal of yttrium aluminium garnet. So that is the crystal which is doped with neodymium, right? So the electrons of the dopant element can be selectively excited to higher energy level, uh, to some high intensity flash lamps. There will be flash lamps uh, which will be used to excite the electrons to a higher energy level. You know. So when this lasing will happen or laser operation will occur. So lasing occurs when these excited electrons return to their normal energy state. So we call it population inversion. So I'm not going into detail as such. Just get the term. So we call it population inversion. Okay. So whenever they will come back to its original normal energy state, or the inversion from the excited state to the normal energy state, at that point of time there will be this lasing action. Now in comparison to Nd:YAG laser, CO2 laser has both high wavelength uh, and high reflectivity. So what is there in CO2 laser? This is a mixture of CO2, N2 and helium. Right? This is continuously excited by electrodes connected to your power supply. Right? So what is problem in laser beam welding? Very high reflectivity of a laser beam by the metal surface. This is a well-known problem. So as much as about 95% of CO2 beam power can be reflected by a polished metal surface, you know. So reflectivity is slightly lower with a YAG laser beam. Uh, so to eliminate or you can't eliminate those disadvantages. So you have to do some kind of thing so that it will be reduced, right? So there is surface modification, so such as there is roughening of operation, there is oxidizing operation, some kind of coating also can reduce this reflectivity. So yeah, those things are there. Then also there is shielding gases, right, to protect your molten metal and yeah. Yeah. Okay, so we will finish over here. Any question?
No, sir.
Okay, ठीक है. So you can ask me any question if you have. So I'll write down my mail ID. Do you have my mail ID? Do you have my mail ID? I don't know. Is it shared or not? No, do you have my mail ID? No. So, okay. So if you have any question, you can contact me. So I'm writing down my mail ID. So if you have any question regarding the session questions, any discussions, feel free to contact. We'll meet again in the next week. Okay? Bye bye.